Okay, chapter 4. Chapter 4 is about introduction to probability. Okay? What is probability? Probability is nothing but a chance. It's a chance that something happened. It's a chance. It's just a chance. Okay? The probability is measured between 0 and 1 and all in between. Okay? You cannot say, I have 50-50 probability. That's not correct. The probabilities are between 0 and 1, so probabilities has to be 0.5. You cannot say 30% probability. No. It's very common, but probabilities are between 0 and 1. It's not 30%. It's 0.3. Okay? Now, 0 means that it will not happen at all. Will not happen. For example, I will never going to win the lottery. 0. That's the probability 0. Why? Because I don't purchase tickets. So the probability that I get the lottery is 0. Probability 1 means that it will happen. It is going to happen whether we like it or not. I'm gonna die. That's probability 1. I'm gonna die. When? I don't know. Later, rather sooner, you know. But I'm gonna die. That's a probability 1. Okay? And in between, any numbers in between. For example, 0.5 is the probability to get a tail when you flip a coin. Right? It's 0.5, 0.5. Considering that having that the coin is in the edge, the probability is 0. Okay? Which sometimes happens, right? Have you seen a coin that when you flip it goes right in the edge? Never? Well, I've seen that. So, but let's consider that probability is 0. Okay? There are a few concepts in probability. We have experiment. An experiment is a process where we are going to observe the outcome. We observe the outcome. For example, flipping a coin is an experiment. And what are the possibilities that we can have? Either head or tail. That's it, right? So that's an experiment. The other is the sample space. This is very important, the sample space. The sample space is the list of all the possible outcomes in the experiment. All possible outcomes from the experiment. So H and T are the only two possible outcomes in flipping a coin. When you roll a dice, you can have either 1, 2, 3, 4, 5, or 6. That's it. Those are the possible outcomes. And all the possible outcomes is the sample space. And an event is a one or more outcomes. For example, rolling a dice. What is the probability that I get less than 3? Okay? That's an event because it can be a 1 or a 2. So those possible outcomes that confirm an event. Any questions? In probabilities, there are three ways to assign probabilities. It is the classical, the empirical, and the subjective. Okay? In the classical way, we assign probabilities depending on all possible outcomes and the outcomes that conform that event. For example, what is the probability that I get a 3 when I roll a die? Okay. When I roll a die, it can be the possible outcome or the sample space is 1, 2, 3, 4, 5, and 6. So I have 6 possible outcomes in the sample space. What is the probability that I get a 3? Just one of these. So the probability would be 1 divided by 6. Why? Because 1 is the number of outcomes divided by the total number of outcomes. That is the classical way. What is the probability that I have a head when I flip a coin? 0.5. Why? Because I have 1 divided by 2 possible outcomes, head and tail. So that is why it's 0.5. It's 1 over 2. That is the classical method, in where you get the chances to get the event divided by the total number of ways that you can get any of the sample space. The empirical method uses historical data. For example, the last 100 times that I've been in Walmart, I spent $43 in, I have 100 data, and I spend more than $43 like 30% of the time. So what is the probability that I spend more than $42? 0.3, because historical data told me that. Okay, so history tells me that. What is the probability that it rains today? Well, I have the data for the last 200 years. And for the last 200 years, only 20% of the time of the days rained. So what is the probability that it rained today? 0.2. Because of the historical data. Okay, so historical data is the empirical way that you assign probabilities when you have historical data. When you don't have the classical way and you don't have the empirical way, you have to use the subjective way. The subjective way is like the gut feelings. What is the probability that you pass this course? Okay? So you're going to tell me, well, the probability is 0.7 because I'm not sure, but it's a subjective. You don't have empirical data. You don't have the classical, I don't have a quota to fulfill in this class or whatever. So it's a gut feeling. I have the probability. I feel that I have 0.7 as a probability to pass this course. So that is a gut feeling. It's the subjective way. Okay? And you use your gut feeling when you don't have any other information. Okay, there are, your book talks about 5 probability rules. The first probability is the one that I told you. The probability of 0, if the probability is equal to 0, the event will never happen. If the probability is equal to 1, the event will happen. The probabilities are between 0 and 1, so 0 less or equal the probability of whatever event less or equal than 1, okay? So the probability goes between 0 and 1 and everything in between. That's the third rule. The fourth rule is that if you add all the probabilities of all the possible outcomes, what it has to be. If you add all the probabilities of all the possible outcomes of an experiment, what the probability has to be? 1. Why? Because there are no other options. There are no other possible outcomes. What is the probability that I have a head or I have a tail when I toss a coin? 1. I have either a head or a tail. That's it. The probability of head is equal to 0.5. The probability of tail is equal to 0.5. If I add these probabilities, it gives me 1.0. Okay? What is the probability that in rolling one die? What is the probability rolling a die? The probability that I get a 1 is 1/6, right? The probability that I got a 2 is 1/6. The probability that I have a 3 is 1/6, and 4, and 5, and 6. What is the total probability? 1. There are no other choices. So if I add all the probabilities of all the possible outcomes, I'm going to have a 1. Why? Because there are no other choices. It happened this or the other. It's, So that is rule number 4. And rule number 5 is that we have what is called the complement of A. And the complement of A is something that is not A. A is an event, so the complement of A is a not A. What is not A? So the complement we have A and we have the complement of A. And in some textbooks they use a C. In this book they use a, how do you call it? Prime. Yeah. No? It's A prime, if you will. The A prime. So if I have the probability of A, then I have the probability of A prime. What is the probability of A prime? Is 1 minus the probability of A. Why? Because the probability of A plus the probability that is not A has to be equal to 1. Because either it's A or it's not. There are no other possibilities. So these are events that are mutually exclusive and collectively exhaustive. That means that nothing else could happen. So the probability of A prime is 1 minus probability of A, or if you want to see the probability of A plus the probability of A prime is equal to 1. It's exactly the same. It's just math. And that's the rule number 5. Now, let's do problem number 4.7. 4.7 says, a total of 200 adults responded to a survey asking them to name their favorite national park. The relative frequencies are as follows. Yellowstone, 33%. Grand Smoky Mountains, 19%. Yosemite, 19%. Acadia, 7%. Other, it says a question mark and a total of 100%. Okay? So they give us the percentage. They said that the total number of respondents in the survey are 200. So N is equal to 200. And we have those percentages. Yellowstone, 33. Grand Smoky, Yosemite, Acadia, and other. Yosemite is 19, this is 7, and other is a question mark. Okay, what percentage of respondents choose the other category? We know that everything has to be equal to 100. So what is this number over here? What is this number? So the only thing that you have to do is to get it the math. Get the math from that number. And 33, 19, 19, and 7. All of these is 78. So it means that this number is 22. Okay? Because everything has to be what? 100. There are no other possibilities. So, what percentage of respondents choose the other is 22%. How many respondents select Yellowstone? 33%, right? How many respondents? So A is equal to 22%. B, how many respondents choose Yosemite? 33% of 200. How many? 66. Because it's the 30% of a total of 200. How many respondents select either Yosemite or Acadia? Yosemite or Acadia? Yosemite or Acadia? Yosemite is this one. Yosemite or Acadia? What is the percentage for the two of them? What is the percentage of these two? 26%. How many? How many respondents? Either Yosemite or Acadia? Even here?
52.
52. You see? Is this an example of classical, empirical, or subjective probability? We have data, right? We have respondents. So what type of probability is that? Check your notes. If it's a classical, it's the possible outcomes. If it's empirical, you have historical data. And if it's subjective, you have no data, but just a feeling. What is this? You have data. You ask 200 people. Okay? What is this? What are these probabilities? Empirical. This is empirical probability. Because you don't have all the possible outcomes, and you're going to say for each of the outcomes, you're going to have the equal probability. Because you immediately know this. For Yellowstone, the majority of the people like Yellowstone. 33% travel to Yellowstone because it cannot be the classical because of the probabilities to visit one of these national parks. It's not the same. There are some places that are favorite for tourists. Right? Okay. The next section is when you have probability of more than one event or two events. And I'm going to raise this, guys. You have two events, A and B. Whatever the events are, could be anything. You have two events, A and B. When we draw what is called the Venn diagram, some of you that you already have probability before, you can have a Venn diagram saying this is A and this is B. And we're going to see what is union and intersection. Okay? Union is when you consider A or B or both. That's union. Is A or B or both. The other concept is what is called the intersection, and the symbol is an inverse U. And the intersection of the two events is when both events happen at the same time. A and B at the same time. So this is the intersection, this is union. And this is called a Venn diagram. A contingency table is when you have a table with the two variables or the two type of possible outcome of the two events, of the two experiment, if you will. And you have, for example, the class and the gender. The gender can be either male or female. And I may have two classes, business statistics and marketing research. Okay? Let's say that in business statistics I have 35 males, 15 females, and in marketing research I have 8 and 12. Okay, so I have two classes, business statistics and marketing research. I have male students and female students, 35, 8, 15, 12. So a total of males is 43, supposedly that they cannot be in the same class simultaneously. 15 and 12 is 27, a total of 50 in my business statistics and a total of 20. So I have 70 students total. 50 in my business statistics, 20 in my marketing research. I have 43 males and 27 females, at a total of 70. So in this case, please consider the probability that I have 100 students in both classes is 0. I either have you here or have you in my other class. So cannot be in the same class at the same time. Okay, now, what is the probability that I have that if I choose someone from these 70 students, I'm going to get a male? The probability of a male. The probability of a male, I have 43, right? And I have 70 students, so the probability is what? 43 divided by 70. That is a probability. And this is classical probability. If I choose one of you randomly of all my 70 students, what is the probability that it's going to be a male? Okay, 43, because there are 43 males of the 70 students total. Okay, what is the probability that it's in my business statistics class? You tell me. How many students in the business statistics class? 50 divided by the total number of students? 70. Perfect. What is the probability that is a male and it is in the marketing research? Male and marketing research. Both events at the same time. What is the probability that is a male and a marketing research student? 8 divided by what? 70, exactly. So I only have 8 males that are in my marketing research class. So the probability that I get a student that is in the marketing research and is a male at the same time, okay, at the same time, and is 8 divided by 70. And so on, so on, so on, so on. Yes?
What's the difference with the union is?
Okay. What is the probability that is in business statistics or marketing research? Is there 35 divided by 43 plus 8 divided by 70, 8 divided by 70. So it's the probability of the union is in A or in B, but and I said that it's not there is no possibility that it's in both at the same time. That's what I said. But if you want to do that, you have to say, and this is the addition rule. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B. That is the addition rule. Okay? But in this case, the probability that are in the same, in the same is totally zero. Okay. I have to raise it. I have very limited space here. We have what is called conditional probabilities. And I'm going to go back to the addition rule and the multiplication rule and so on, just a moment. Conditional rule. Conditional probabilities, I'm sorry. Conditional probability, it is said the probability of A given B. This is a straight line, vertical. Okay? And it's read the probability of A given B. The probability of A given that B already happened. Okay? B already happened. That's what is the probability of A given that B already happened. Okay? So the probability, this probability is equal to probability of A and B divided by the probability of B. Okay? Why? Because now my universe is B. The total universe is B because I know that B happened. Okay? So the probability of A given B is the probability that the event, the intersection of the event happened, A and B, divided by the probability of B. Going to the contingency table, I'm going to say, what is the probability that is a male given that is in a business statistics class? What is the probability that is a male given that is in my business statistics class? Okay? If you have your contingency table, business statistics is 50. So I know that I pick students from the 50. And marketing research is 20. So 20 is not part of the marketing research, so my whole universe is 50. So it belongs to business statistics. What is the probability that it's a male, given that it's a business statistics? It has to be equal to 35 divided by 50. So it's the probability that is male and in business statistics divided the probability that is in business statistics. Okay? You see? So the probability of A and B divided by the probability of B is the probability of A given B. Okay? What is the probability of B given A? The same thing is the probability of A and B divided the probability of A. Why? Because right now the A is my universe. So you have to be very careful on this. The probability of B given A is the probability of A and B divided by the probability of A. The probability of A given B is the probability of A and B divided by the probability of B. Right? Why? Because we know that it already happened. The given that already happened. So we have to start from that particular point. Right? Now, we have mutually exclusive events. Mutually exclusive. Mutually exclusive events are events that cannot happen together. Okay? It means that the probability of A and B is equal to 0. The probability that the two events happen at the same time is equal to 0, by definition. Okay? Now, we know that the probability of A and B is equal to probability of A given B times the probability of B, right? So, if, hold on just a second. In mutually exclusive events, let's start right there. I mean, let's start right there and saying that the probability of A and B is equal to 0. We have what is called independent events. By definition, independent events are those events that do not interfere with each other. It's independent. So the probability of A given B is equal to probability of A. That's by definition. So if I flip a coin and I have a tail, what is the probability that I have a tail next time that I flip the coin? What is it? What is the probability? Okay, I flip a coin and I get a tail. I want to flip it again, and what is the probability to have a tail? 0.5. So the events are independent. It doesn't happen. It doesn't matter what happened before. The probability of A given B is the probability of A. It really doesn't matter what happened with the other event. The probability is independent for what happened with the other event. Now, can two events be mutually exclusive and at the same time independent? Yes or no? The answer is no. No, we cannot have mutually exclusive and independent events. Because if they are mutually exclusive, they are dependent. They're not independent. I mean, if one happens, the other is not going to happen. They are dependent events, so cannot be both at the same time. It's easy to say, well, if they are mutually exclusive, they are independent. No. If they are mutually exclusive, they cannot be independent. What is the probability of A given B if they are mutually exclusive? 0. They cannot happen together. So cannot be, independent. Cannot be independent. So, and the definition is that if the probability of A given B is the probability of A, then we have independent events. If it's not, then we have non-independent events. And that comes the addition rule and the multiplication rule that is part of this stuff. And we're going to do a few problems and then that's it. An addition rule is the probability of A or B is equal to probability of A plus probability of B minus the probability of A and B. And it's obvious. Why? Because if you draw this, and this is A and this is B, you are considering the probability of A union B is all this, right? So the probability of A, the probability of A, no, let me do it. Orange. The probability of A is this, right? The probability of B is this one. I'm sorry. But you consider twice the probability of A and B. You consider it in A and you consider it in B. So you have to subtract the probability of A intersection B. And that is the rationale to do this. Okay, and that is the addition rule. The multiplication rule and it comes from the probability of A given B is equal to probability of A and B divided by the probability of B. Right? So the probability of A intersection B has to be equal to the probability of A given B times the probability of B. Right? It's just common math. The probability of A intersection B is equal to the probability of A given B times the probability of B, and is also equal to probability of B given A times the probability of A. So it's exactly the same. That is the addition rule. This is the multiplication rule. The addition rule tells you what is the definition of probability of A union B, and the multiplication rule tells you what is the probability of A intersection B. Now, what happened when I have independent events with the multiplication rule? In independent events, the probability of A intersection B is equal to the probability of A given B, but if they are independent, the probability of A given B is the probability of A. So, the probability in independent events, the probability of A intersection B is the probability of A times the probability of B, because these events are independent. Okay? In mutually exclusive events on the additional rule, the probability of A union B is equal to probability of A plus the probability of B. Why? Because the probability of A intersection B is equal to 0. You see? So, that is how you identify the mutually exclusive events and independent events. Any questions? Okay, let's do a couple of problems. Let's do, which are not in this, in the house. Okay, 417. 417, it says, what's that 417, please? I don't know. Consider a standard 52 card deck from which one card is randomly selected and not replaced. Then a second card is randomly, so I get a card from the deck, and then I get it aside and get another card. Okay? Define the following events. The first card is define the following events. A is the first card is a heart. B, the second card is a heart, and are these two events mutually exclusive? Why or why not? Okay, so the events are getting a heart from this, from the deck. And the second, the event B is getting the second card also a heart. Are these two events mutually exclusive? Okay, go to the definition. Can
You don't
those?
put the card back, so the chances change.
Exactly. So indeed, they are not independent events. They are not independent events because if I get a heart in the first card, my probabilities of getting the second card a heart is going to change. Right? So they are not independent. We know that these events are not independent. Are they mutually exclusive? Can I have a heart in the first card and then have a heart in the second card? Yes or not? Yes. So they are not mutually exclusive. You see? So that is the definition, and that's what
Wait, they are mutually exclusive?
they are not mutually exclusive. They can happen. I mean, I can have a heart in the first card, and I can have a heart in the second card as well. So the probability of given that I have a heart is not zero for the other event. Okay? So they are not mutually exclusive. The probability that both events happen at the same time is not equal to zero. Okay? So they are not mutually exclusive. Are they independent events? No, because when I get a card, if I get a heart, the probabilities for getting a heart the next time the second card is going to change. It's not anymore the same probability. So they are not independent events. Okay? So the probability of A given B is not the probability of A.
You said A was what now? First call?
First card is a heart.
Okay, and what was the answer?
The answer is no. They are not mutually exclusive and they are not independent. Okay? Let's do another one that is probably a little bit more challenging. It's 419. In 419 it says, a local car dealership currently has 36 used GM, Ford, and Toyota vehicles. So we have a total of 36 vehicles, right? This is 419. So we're trying to figure this out. 419. We have GM, Ford, and Toyota, right? And we have, can be either cars or trucks, okay? That's it. No motorcycles, no three-wheelers, no whatever. So either cars or trucks. Okay, those are the possibilities. The make of the model and either it's a car or a truck. It says 26 vehicles are cars. So a total of 26 are cars. 11 vehicles are General Motors. 11 total, 11 vehicles are General Motors. 15 vehicles are Ford. Okay? We have a total of 36, right? Remember? 14 vehicles are, what did you say? 15 vehicles are Ford. 3 vehicles are both Toyota and trucks. Toyota and trucks are 3. Am I right? Yes. 14 vehicles are both Ford and cars. Ford and cars, 14. Now, they start asking questions. Okay. Whew. How many? We have 36 total, and here we have 26, so we have 10 Toyotas total, right? I'm just filling the blanks. 10 over here. If I have 10 over here, I have 7 that are cars and Toyotas, right? If I have 15 over here, then I have 1 truck that is Ford. Okay? If I have 26 right here because of the number of cars, then I have 21, I have 5 General Motor cars. And if I have 5 General Motor cars, how many trucks? 6. Oh, I'm sorry. Oh. If I have how many trucks? 10. So you see, the pink numbers are the ones that the program didn't give us. And that's probably the toughest part of it. What is the probability that a randomly selected vehicle is a Toyota? What is the probability of a Toyota?
36.
What is a Toyota? How many Toyotas we have? 10. How many total? 36. That is the probability. 10 divided by 36. What is the probability that a random selected vehicle is a truck? The probability of a truck. How many trucks? 10 divided by 36. You see, so once you have your contingency table, the rest is pretty easy. Once you have your contingency table, the probabilities are pretty easy. See, what is the probability that a random selected is either a Ford or a car? Or a car. Go to the what? What is this? Ford or car. So it's a union. Go to the addition rule. If the probability that is a Ford plus the probability that is a car minus the probability that is a Ford and a car. Huh? You see? Because that is the addition rule. Check your addition rule. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A intersection B. So what is the answer? I don't know. Let's see. What is the probability that is a Ford? 15 divided by 36. Plus the probability that is a car. 26 divided by 36 minus the probability that is a Ford and a car. 14 divided by 36. That is the answer. See? So that is why it's so important to have the addition rule and the multiplication rule. In this case, you use the addition rule. What is the probability that the random selected vehicle is a GM truck? D is pretty easy. GM truck. Probability that is a GM and a truck. GM and a truck is 6. 6 divided by 36. You see? Ooh. What is the probability that the random selected vehicle is a Toyota given that it's a car? Given a Toyota, given that it's a car. That is the probability of it's a Toyota and a car divided by the probability that it's a car. This is a multiplication rule. Okay? So what's the probability that it's a Toyota and a car? Is 7 divided by 36 divided by it's a car. 26 divided by 36. So it's equal to 7 divided by 26. That is the probability of it's a Toyota given that is a car. is a truck, F, what is the probability that the vehicle is a truck given that it's a Ford? Given that it's a Ford, the same thing. Is the probability that it's a truck and a Ford divided by the probability that it's a Ford. A truck and a Ford is 1/36, and the probability that it's a Ford is 15 divided by 36 is equal to 150. You see? It says construct a decision tree for these events. You want me to do that? Let's do that. It's, I mean, a tree diagram is nothing but going to branches. You start here and you say, well, it's either a car or a truck. When it's a car, it's either a GMC, a Ford, or a Toyota. And if it's a truck, it's either a GM, a Ford, and a Toyota, and then you start, building the probabilities. And at the end, when you add all these probabilities, it has to be equal to what? 1. There are no other possibilities. The probabilities of each one of these branches has to be equal to 1. And of course, this is equal to the probability of GM and car. This is the probability of Ford and car, and this is the probability of Toyota and car, and this is the probability of GM and truck and so on. And if you add all those probabilities, it has to be equal to what? To 1. At the end, if you add these probabilities, and if you don't get the one answer, it means that there's something wrong. Okay? But this is the tree diagram. I'm going to stop right here. Let me assign you the